Okay, we're back, we're live, we're here for, I guess this is a science show. This is ThinkTech Talks, and we're talking about science. We're talking about astronomy. We like to talk about astronomy. We've had many shows with the Institute for Astronomy, but this is a special show at a special time. With Doug Simmons, he's director of the Canada-France-Hawaii Telescope, and Rich Matsuda, he's an engineer with the Keck Observatory. Welcome to the show, you guys.
Thanks for having us.
Great to have you here. It's great to be able to discuss in the clear air, if you will, what's going on the top of Mauna Kea. I think the public needs to know about that, and I am just delighted that you're here, that we can talk about it. So we're going to talk about the status of the observatories on Mauna Kea. If you don't know about it, you should listen carefully, and what has been going on there and what it looks like going forward. For astronomy, for Mauna Kea, for you guys in science. Great to have you. Anyway, let's begin at the beginning. So we've had, all this noise and tumult about the top of Mauna Kea and all the TMT, 30-meter telescope there. My own background on it is that about 7 or 8 years ago, when I was doing programs for the Hawaii Venture Capital Association upstairs in the Pioneer Plaza, in the Plaza Club, we had a show, a luncheon speech by a woman who was representing TMT and who came out here to start the permitting process. Mm-hmm. And she said, I remember it so well, we probably have it on tape, that this was going to be a really big project involving a lot of money. They had a lot of experience in arranging permits wherever they went. This was a very important project for them because of the quality of the observatory environment. And that they were going to cross every T and dot every I, and we would see this, come into place in due course. I was very impressed with that because she was a real professional, and although she wasn't from Hawaii, I thought she understood a lot about what happened in Hawaii. Now we fast forward, it's almost 10 years actually since that time, and we still haven't actually broken ground. Am I right?
Not in terms of actual construction activity.
Yeah,
that's right. There was a groundbreaking ceremony attempt, but the actual construction really hasn't started yet.
Yeah, I heard that too, that when the groundbreaking ceremony was established, even though, the permit had been obtained, she said exactly, she did exactly what she said. The permit was obtained, all the legal requirements have been satisfied, they were free to construct, and there was a groundbreaking ceremony, and it didn't take place because there were protests about it. And the university just canceled it and elected to go ahead with construction. But at that point, there were more protests. So, and then the governor got involved. We all saw that in the paper a few weeks ago. Mm-hmm. And I had the sense, I still have the sense, that it's locked up. Am I right?
It's locked up in the sense that there's no clear vision forward. And I think that the broader community understands where we're headed. It's not locked up in the sense of hopelessness, though.
Oh, no.
I very much ascribe to an approach that through a lot more dialogue in terms of number of people and in particular engaging community members that so far haven't really been engaged in that discussion, that we're going to find a path forward.
Well, I thought, actually, I'm making it clear, neither of you guys are with TMT. You're with other
correct.
Telescopes down, in that area.
Yes.
But you, certainly you care about what happens with TMT. Mm-hmm. You want your community to be, able to go forward on these projects. But, I thought that in all this time, 7, 8, 9, 10 years, whatever it was, where TMT was dotting all the I's and crossing all the T's, and thus did actually get, there were plenty of public meetings. There was plenty of opportunity. People expressed themselves. Did I miss something here?
No, you didn't, but I think the new dimension that's come into play is that there's a relatively young generation. And in fact,
they weren't around when this woman spoke to us.
Correct, and exactly. And that generation is in large part a product of the Hawaiian Immersion School system, which is relatively new. And what they have gathered from that education system, they're applying in very real terms to their home on the Big Island. So you take that new dimension, you multiply it by social media. I mean, these are kids that literally could be my kids in terms of age, are tech savvy and able to really amplify that through social media. And you have a very different situation than you had, say, a decade ago, when that individual was starting to think through all the steps that had to take place to actually get to the point where you could have groundbreaking and construction. So things have changed in that sense.
Well, it's one of many ironies, but one gigantic irony. You know, ThinkTech, we follow tech, that's our middle name. Right. And we care a lot about tech. We think tech can make the world a better place. And in some ways it does. In some ways, maybe it isn't fully appreciated. But here you have a generation that is consuming tech like no generation before. And they don't seem to really understand the science and technology that is on the top of Mauna Kea. It is probably the greatest state of science and technology in our state, bar none. You know, the nexus between Mauna Kea and the Institute for Astronomy on Woodlawn Drive at UH, this is huge. And there's another facility right at Hilo. This is huge, and it is pure technology. It is pure science. It is the top of the line. Why don't they understand that?
Oh, if you want to dive into this,
okay, go for it.
Hog it all.
So I think maybe we're missing some connections here, and maybe I can explain some of those connections. So it may seem that we're just looking up at the stars, but as you mentioned, there's a lot of technology involved. So some of the camera technology that we use at the observatories and our instruments, that technology actually relates very closely to the camera you have on your cell phone or the camera you have in your pocket. The way we track stars and the coordinate systems we use to do our science, very relevant to satellites that everyone depends on, right? GPS satellites and communication satellites and satellites that look at and monitor weather on Earth. There are so many connections, I think.
Are you inventing this technology for use by others, or are you using technology that was invented for other purposes in your astronomy, or both?
I think it's a mix of both. I think you can say in both cases that pushing the technology forward for astronomy has benefited other areas as an offshoot. So one example is astronomers figured out how to use images from multiple telescopes to create a single composite image, and that kind of technology is used on MRIs and CAT scans and things like that. There are many applications that relate to practical things.
Now, I've heard, just in the way of exploring the science involved, that the important thing is not so much anymore the lens as it is the sensors that read and process the light. Can you tell me where we have been going in the technology on that issue?
Do you want to take that?
Well, it's been revolutionary, and you're exactly right. The way that these observatories maintain a state-of-the-art edge is not through the telescope per se, it's through the instrumentation you put on at the focal plane. And for example, the infrared arrays we use now, which I'm very proud to say carry the acronym Hawaii because they were developed in conjunction with the University of Hawaii's development program. These have millions of transistors built into them. They're roughly an inch on a side. An incredible technological feat that you can...
Did you say millions?
Millions
Okay. That's a
of
lot of
transistors packed into that package, that's right. And they operate at cryogenic temperatures, and they have sensitivities that are unprecedented. And that's all technology that has a lot of spin-off. That's why these companies that generate it, in particular Rockwell and Teledyne and Raytheon, this isn't necessarily a money-making, astronomy is not the path forward for these big companies, but by developing this technology and pushing it to the edge, they learn new things that they can apply to the commercial companies that they actually use to make a profit out of it all.
Yeah, this is really important. You've touched on something really important. It's the why question. You know, as I suppose you could ask that about going to the moon, sending space shots, which Hawaii is involved in. I guess we have a question. Let me just turn that off.
They're after you.
By the way, if anybody wants to send in a question or comment, yes, we can handle that. We will answer any question, right, you guys? We will answer any question. So you can send it to us at our handle, our Twitter handle, ThinkTech Hi, H-I, okay? So let's have those questions. We'll be able to see them on the screen. Why do we go to the moon? Why do we go to Mars? Why do we do these really amazing romantic things and spend a lot of money in the process? And I think that astronomy and Mauna Kea and these telescopes must be in the same, it's something about mankind, humankind, reaching out to the stars, finding about things we would never know about, pushing the boundaries of our own consciousness, collective consciousness. But you tell me, I mean, why we do this, and as you said, is it profitable?
No.
Astronomy,
Astronomy,
how does
trust
it work?
me, you should see my truck.
Nonprofit.
It's not, astronomers don't do this to get rich because it just doesn't work that way. I think the answer to your question is unique to every person, though. Why is it important? It is a personal sort of process of figuring that out. For me, when I kind of drill down as to why is it important to me, I've come to the conclusion that it's all basically an exploration of ourselves. It provides a context and a meaning for exactly who and what we are and what I think of as a grand and elegant universe. And I really look forward to the discovery horizon that I believe is within this century that will rewrite our understanding of what reality actually is. This is really deep stuff. We're borderline physics and philosophy when you think about it.
Alex Filippenko, he was here 6 or 8 months ago, amazing mentality. And he spoke at the university. And I'm sorry, I didn't know much about, I couldn't understand much about what he was saying, because astrophysics is not something you talk with your wife about at the breakfast table.
I can vouch for that.
But he had these kids come in, and these kids were 8, 9, 10 years of age, asking him questions. I didn't know what the question was, much less the answer. But what we're going into a new place with this.
Right.
And the generations to follow will be able to relate to it. And you're really at the bridge.
That's right.
That's what's happening.
That's right. And it's an amazing frontier. It's a combination of what we call precision cosmology and our ability to precisely measure things about the fundamental nature of the universe.
Hairdressing. He made fun of that.
Yeah, nothing to do with that, sorry. High energy physics, the particle accelerators, it's all coming together in a radical, complete new picture of the universe. And this is part of kind of the gift of our generation to the future generations. I kind of view my role and Rich's role to provide the tools and the framework, and then it's the next generation that we want to inspire to take that next step and crack the code.
Wow. And we're here.
It's cool.
We're here, we can see it, if we take a moment, we can understand it, we can relate to it. You are our agents, our heroes, our champions. Find out where humankind is in the continuum of the physical and astrophysical universe. It's fabulous. And here in Hawaii. So Mauna Kea is special in a global sense. Can you tell me how special it is? Where do we fit in a global effort to answer these questions?
So Mauna Kea is very significant, but I think in a broader perspective. So as you can tell from what Doug's just said, it's very important scientifically. It's the best site on the planet, I should say in the northern hemisphere, maybe the entire planet.
Why?
For doing astronomy, because it's in the middle of the Pacific, so very stable. The shape of the mountain is such that the wind flowing over it presents a laminar flow, so there's very little turbulence. It's up above 40% of the Earth's atmosphere. It's in a very rural location, very little light pollution. So there are all those aspects, and as you know from the issues...
It must be beautiful up there.
It's beautiful. It's spectacular.
It's unbelievable to see the starry sky from a place like that.
Right.
Wow.
But,
Anyway,
but I think it's not only limited to science, as you can tell from the issues and how the community is reacting to what's going on up there. It's very significant culturally.
Why is it significant culturally? I mean, my reaction now is that before TMT, there were 12 telescopes up there. 1, 2, 3, right? I get that right?
13?
They're currently,
13, and
Okay.
TMT would be the 14th.
I think it's 12 and
I'm
TMT
sorry,
is the
you're
13th.
correct.
Okay, whatever.
Yeah.
And that seemed fine. Everybody was good with that.
Mhm.
That started in after the beginning of the 20th century sometime. And it was famous, increasingly famous over all the years of the 20th century. Nobody said boo about it. Now all of a sudden it becomes a cultural icon. What happened?
I wouldn't say nobody said boo about it. I think that's
Right.
not being fair. I think there's always been a profound sense of connection within the Hawaiian community for this site, and I certainly respect and honor their perspective that it is a sacred site. And I think we all have to have that perspective in figuring out how we go forward.
What's sacred about it?
I think we need to have the Native Hawaiian community here to answer from their heart
What do you
exactly
know?
what is
What
sacred
are
about
they
it.
saying about it?
It's in essence a connection point to the rest of the universe. It's the high point in all of Polynesia.
Because it's a high point.
Because it's a high point, and because it has this sort of a pico aspect of the umbilical cord for their beliefs that make it a connection point to essentially everything across the Pacific.
Is there any reason why these two things, that is the cultural iconic quality of this mountain, actually there's two mountains involved, you know, and the highest science in the world can't coexist? Is there any reason?
I certainly subscribe to the belief that they can coexist, and that's the path forward. Exactly how they do that, I'm not sure. And I've repeatedly put myself sort of out there in the sense that I'm a Catholic, and there's a spiritual dimension to me, and I'm a trained scientist with a lot of math and physics. And for me, those actually do intersect, and it gets back to this concept of exploration of oneself, and they're in complete harmony with me. And that gives me confidence that others who kind of do that sort of drilling down in exploration will find that they actually do intersect if you just follow those two paths long enough in sort of an introspective fashion.
That's what we're here for.
Correct.
And Richard.
Getting pretty deep.
So that's right. Okay, this is ThinkTech Talks. We're talking about the future of astronomy in Mauna Kea and in Hawaii with Rich Matsuda, engineer with the Keck Observatory, and Doug Simmons, director of the Canada-France-Hawaii Telescope. You're not Canadian.
No.
And you're not French.
Nope.
We're going to
Can't
ask
tell from
you
the accent.
how that works. We'll be right back after this break.
Hi, I'm Ethan Allen. I host Likeable Science on ThinkTech Hawaii, and I do this because I care about science literacy in Hawaii. I want to spread the understanding that science is a vital and interesting part of everyone's life. I want to make sure the broadest possible spectrum of people understand the beauty and the value of science and realize that science plays out each and every day of their lives. I want you to understand that science is fun. So we bring onto this show each week guests who are scientists, from astronomers to zoologists, and we talk about what they do and how they do it. But most importantly, we talk about why you should care about their work, why you should see that their work has value and impact on your life. So I hope you'll join us Fridays, 1 p.m. here on ThinkTech Hawaii. You can watch us via live stream. You can watch us recorded on Olelo, and you can see us each week. We hope you'll join us.
Global thing, we'll go to the pictures. Sure. Okay, we're back, we're live. I'm Jay Fidell. This is ThinkTech Talks, talking about science, talking about the future of astronomy at Mauna Kea, with Rich Matsuda and Doug Simmons, one from the Keck Observatory, which is one telescope, and the other from the Canada-France-Hawaii telescope. How big are your telescopes, by the way?
Keck telescope, there are actually two telescopes. One that went into science in 1993 and the second one in 1996. They're both 10-meter diameter. That's the usual way we measure. It's the width of the
10
primary.
meter would be the
width of the primary mirror.
The primary mirror,
Yeah.
or mirrors.
In,
So you
in
have
Keck's
one
case,
mirror, though, huh?
actually, it acts as a single mirror, but it's made up of 36 segments that are pieced together to form what looks to be a single mirror. And that segmented technology, you were talking about what kind of technology developments have we done on Mauna Kea, and that segmented technology, which Keck put into practice, is the technology going forward for TMT, which has 400 and something segments, and for Space Telescope, next generation. And so technology that's developed on Mauna Kea goes globally as well.
Yeah, sure. And those mirrors, the ones that you have, they're not that big, huh?
They're about 1.8 meters
1.8
in diameter,
meters.
so fairly big.
4 feet or so?
Yeah.
No, more, 5 feet maybe, huh?
You're right.
And
they're about that thick.
And they move. They're computer driven, and they
Correct.
move and change. And so you can take all of those hundreds, or in your case,
36.
36, but in the case of TMT, hundreds of them, and you can shape them into one big mirror by
That's correct.
moving each one in a coordinated way with pretty sophisticated algorithms in a computer somewhere.
Yes.
That's really interesting part. Okay, let's go to the Canada-France-Hawaii telescope, or telescopes.
So we are a 4-meter class telescope, about 36 years old now, so considerably older than Keck.
Are you envious?
No, not at all. I have no aperture envy to share today.
Aperture, and you got it.
So it's a different type of design. CFHT's primary function is to serve as a wide field panoramic telescope, and Keck is a relatively narrow field telescope. And this is one of the synergies that we kind of hinted out before. So CFHT has both an optical and infrared panoramic camera, or camera systems, that we use to map out large regions of the sky. In fact, we just completed a couple of years ago something called the Legacy Survey, which has 40 million objects in that catalog we generated. And that's kind of the seed from which you can sift through all of that. You can mine through that data and generate interesting targets based upon our observations.
And
Then
what's an object?
A galaxy, an unusual star, something with unusual properties, basically. It could have an unusual shape, unusual spectrum associated with it.
Exoplanets?
In principle, if you observe it over successive periods of time and you track its motion across the
I'm
sky.
only saying this because I know a kid at Iolani who discovered an exoplanet, and he won the science fair because he did that.
Yeah,
That's cool.
So, but our role, in a sense, our specialty is to generate these large numbers of interesting potential targets, and then you have the Kecks, and the same principle applies to TMT, in that we're basically providing interesting feeder targets to what is the ultimate microscope on the sky, which is a facility like TMT.
Okay, so this is pretty exciting. And it's going to, presumably, if permitted, it will continue to do this kind of leapfrog evolution, looking at the whole sky, looking at parts of the sky, looking at both whole and parts, and taking advantage of the newest technologies. But that sounds like a global, initiative. And from the names of these Canada-France-Hawaii, France-Hawaii telescopes, Keck, and the consortium in the 30-meter telescope has to have about 5 parts to it. It's what, 1.6 billion? I forget, but it's a lot of money. So we see here unfolding capital and scientific talent coming from all over the world. Can you describe that and where Mauna Kea fits in that, global process?
You want me to take it?
Yeah, go ahead.
So you're right in the sense that it is a highly international enterprise. And in a global context, Mauna Kea observatories are #1 year after year, as opposed to, for example, their Chilean counterparts. And that's something it's very important our viewers understand, because this is something we in the state of Hawaii should be proud of. This is a unique scientific accomplishment that through this international collaboration, where the entire world recognizes Mauna Kea as a unique site for astronomy, is able to give us this sort of international prestige and stature that is unlikely to come about potentially in any other way. I see this as truly the legacy class contribution to society at large through the research being done on Mauna Kea.
Where are you guys trained?
I went to the University of Washington,
Studied?
electrical engineering.
Always a good start for everything.
And I worked at Boeing for about 8 years. And working at the observatory was my chance to come back home. I grew up in Honolulu.
Yeah.
So it's been great.
Yeah.
And I have several colleagues at Keck and at Canada, France, and other telescopes that kind of have taken similar paths.
Yeah, great. You like your career?
I love my career.
Yeah.
Yeah.
Doug?
And I got my bachelor's in astronomy at Caltech, and then came to UH to get my PhD. My first job was actually at Canada, France, and that was as a resident astronomer. Then I went to Gemini for 18 years and had the pleasure of being the observatory director the last 5 of which, and then came back home to CFH. So his point is something to be emphasized, in that a lot of us have worked at multiple observatories. So in that sense, it's a great opportunity because there's such a collective sense of ownership, and there's so much depth that we share across the observatories. It's a very collaborative, collegial environment.
Cross-pollination.
A lot of cross-pollination going on. That's right, in so many different ways.
So, and so you guys know each other because what? You work with each other? Or
We're separated by a traffic light in downtown
Right.
Waimea.
Okay. You do a lot of work. You're not up there at the telescope all day. I think people don't understand that.
No.
You don't have an office and, you know, and all this and a whole, a whole facility up there where you work all day under the lens or something. It's not like
no.
that.
In fact, it's very challenging to work up there because of the altitude.
Yeah.
So we have a very dedicated staff, very talented staff that works up there. And they're specifically, like in Keck's case, maintaining equipment or getting ready for tonight's observing. In fact, our crew right now is putting the final touches on getting ready for tonight. The rest of the staff, I think one thing people don't realize is, so Keck staff is about 120 people. Probably 85% of those people are not astronomers. They're engineers, technicians, administrative staff, and I think that's very similar numbers to our percentages.
How many are local?
So at Keck and probably across the observatories, I would say about half of the people are hired in Hawaii. So they lived in Hawaii when we hired them, and about half from the mainland or outside.
Mm-hmm. So when you say you work together around the traffic light, Waimea, that's a great place to be there. I didn't know they had a traffic. Well, I guess they do.
It's been
They have the
upgraded.
shopping center, right?
That's
Right.
Okay. So you're going to compare notes. You're going to compare scientific notes. You're going to talk to each other about your respective efforts at your respective telescopes. Is that what happens?
It's more than that. It's that when we need to help each other out, we do. That's the level of collaboration. Some of the most impressive collaboration I saw was after the 2006 earthquake, where we had each other. I mean, Keck took a big hit. I was the Gemini director at the time. That was unprecedented. And literally at the level of the directors, we were promising each other, we're going to help you out. We've got our own situation. It felt like, kind of a mini disaster. And
Well, what happened? What damage was there?
well, you
We
can
had-
describe Keck's
Yeah,
situation.
so Keck, the telescope structure, how it's held onto its bearing journal, got really damaged. There was an instrument that got damaged. There was, a lot of physical damage.
These instruments, I mean, telescopes in general, are fragile, no? They're high-tech, they're fragile.
It's an interesting combination because they're the domes and the telescope structures are big industrial things, and then you have very fine instrumentation, delicate instrumentation riding on top of those things, and it's a combination of
You
both.
have to watch it, you have to maintain, you have to manage it as complex equipment.
You're taking a 300+ ton telescope and trying to
Move it around
control it and
1
move
inch.
it to a nanometer
Yeah,
precision.
not an inch would be easy.
Yeah.
No, this
Oh,
is
less
to,
than an
Yeah,
inch.
it's
a fraction of an arc second on the sky
Oh my gosh.
Right.
is the level of control. And this is a big structure to be moving at that level
So
of finesse.
TMT has some very high technology things in that same.
Yes.
I mean, I've seen animations, and drawings of what it's going to look like, and it looks like it's very high tech in terms of moving around, of pointing one way or the other. It's got a whole field of vision, doesn't it, from every side of the horizon to do that. So money, money, money. These things cost a lot of money, and my sense of it is that that it's not just University of California. It's not just Canada or France. It's not just Japan. It's many, many, many countries, all of whom are involved in science, all of whom want to see these projects succeed, and they raise money everywhere they can. And the result is, I mean, after a lot of effort, I'm sure, the result is popular guy today. I don't know why people call me when they know I'm on the air.
Because they know you're on the air.
Or why it keeps on going after I turned it off. How much money is involved, would you say, for your instruments and for the top of Mauna Kea? And how is that raised? And what kind of financial arrangements do we have to raise it? Is it easy? Are there big checkbooks out there waiting to write
I
a check
wish.
for any amount
Yeah.
in order to fund your efforts?
It's definitely not easy.
No, it's not easy. The capital investment to date is about $1 billion in the collective, what we call Mauna Kea observatories. And it is the largest collection of observatories in terms of power ever assembled. And that's how you get this sort of #1 stature internationally, scientifically. So it is a big investment, and you're right, it's been piecemeal over the years. It's basically only through national federal funding agencies that you have that kind of long-term investment possible. The construction cost is one thing, but as you well know, the mission cost is dominated by operations integrated over the lifetime of the telescope. And for that, you need a revenue stream, so to speak, coming from federal governments. We don't actually have any revenue coming in or out
It's
of
not
this.
like you're selling widgets on the
No,
street corner.
no, we do not
You
sell
have to be
telescope
funded
time.
for everything you do.
That's right.
It sounds like ThinkTech, actually. So you're always worrying about the next dollar.
We
You're
are.
worrying about the next fiscal
So
period.
my
Yes.
annual budget is about $7 million. Most of that goes into labor to keep my staff employed. Minimal amount in capital. We have electric bills, all that type of cost associated with it. And our job too, when we administer the observatory, is that on December 31, we basically draw down to zero. Generally we can hit it within a percent or two. We have to be kind of on top of it. And then we seek an additional 1-year allocation of funding from our federal funding agencies, and then we work our way through that budget. So it's really important to understand these are not revenue generating systems. These are paid for by federal entities like the National Science Foundation, the National Research Council in Canada, CNRS is the acronym in France, and it's at these federal levels that the money comes in, and has been pointed out by Rich in other discussions today. Where do you think that money lands? It lands on the Big Island and in the state.
Sure, it's where it's spent.
Exactly, exactly. So it's a very valuable, resource that we should appreciate.
So if I come to you and I say, look, I got rights here and I want $1 million a year, to let you do your thing, you're going to have to go out and beg, borrow that money. You're going to have to get that money from these funding sources.
We have to justify ourselves every year. You better believe it. And I've been on the front lines of that for the past 8 years.
Yeah, but
as
if
an
I come to
observatory
you and
director.
say, I won't protest you anymore if you just pay me a rent of $1 million a year, you're going to have to go the
You have
same
to find a
route.
way to.
You have to squeeze that pot all the more. It doesn't come off a tree.
No.
Right.
No.
There are no trees at that altitude anyway.
That's true.
No. It's a competitive funding environment, particularly when you think of the NSF, which is about a $7 billion annual budget. It's the largest science foundation in the world. Guess what the astronomy budget is out of the NSF? You tell me. What do you think?
Operating budget.
The annual operations cost for research grants and operating facilities.
Okay, I'm gonna take this break to consider your question. And when I come back, I may have an answer for you. That's Doug Simons, Director, Canada, France, Hawaii Telescope, and Rich Matsuda, engineer at Keck Observatory right down the road. And we're talking about From the Top. That's what I originally named this show. From the Top, the future of astronomy at Mauna Kea, here on ThinkTech Talks. We will be right back. And I'll try and answer that question.
Aloha, I'm Hunter Hevlin, host of Sustainable Hawaii here at ThinkTech Hawaii. You can tune in every week on Thursday at 2 p.m. to see interviews with sustainability professionals from around the state and even further abroad, learning about activities with water management, food security, waste management, and a whole host of other fascinating opportunities to get engaged with making a greener island. So if you're interested in making the transition from consuming individuals to communities of producers, check us out every Thursday.
Hi, I'm your host on ThinkTech Asia, Bill Sharp. I look forward to you joining us each Monday between 4 and 5 o'clock when we film right here in our studio in downtown Honolulu. The show, ThinkTech Asia, focuses on contemporary events in Asia. And by Asia, we mean anything from Hawaii, south to Australia and New Zealand, west to Pakistan, and as far north as the Russian Far East. Clearly, this is one of the most economically dynamic centers of the world, and we bring you up to date on what's going on in a whole host of countries in this very vital region. We look forward to seeing you.
What happens in
Aloha.
Christmas future? Would be,
Good question.
well, I'm going to try to answer that question. I would say 500 million.
You're surprisingly close. You're a factor of 2 over, at 250.
250. You guys have to sweat with only 250
Out of a $7
to cover.
billion budget, the federal astronomy budget of the NSF is about $250 million. That's how tight the funding is.
Yeah. Was it more before?
No, it's barely kept up. In fact, in recent years, it has not kept up with inflation.
So I thought you said you really liked your work.
That part's difficult.
Because that's spread around,
Right.
for all the activities. You're not
That's
getting
right.
much out of it.
Yep.
Yeah. Okay, well, let's go to the pictures and see what they look like, and we'll try to get a hand on exactly what we have there at the top of Mauna Kea. You guys can describe what we're seeing.
Rich?
That's a picture of the Keck telescopes, both of them in the bottom right corner looking up at the Milky Way. And you can see one of the telescopes is projecting a laser beam, which is part of our adaptive optics program.
Wow, so why do you have does that help you see it?
Yeah, so adaptive optics is a system meant to take out the blurring effects of the Earth's atmosphere. So you get this perfect wavefront coming from some star far away, and it travels all the way to Earth, and then it hits the atmosphere and gets all messed up because of turbulence in the atmosphere. So you can correct for that by looking at the star and seeing how it's moving in the sky, the twinkle of the star, and take the twinkle out. But there aren't enough stars in the sky that are bright enough to do that. So we use a laser to create an artificial star. So we send a laser beam going up at 589 nanometers, and it causes the sodium layer in the atmosphere to fluoresce and create a artificial star that we can correct off of. So
Should you take this picture with your iPhone?
Obviously not.
It's beautiful.
Yes, I think one of the professional photographers
Okay, got
we
it.
hired took that
Beautiful.
picture.
Okay, what's next? It's a video.
Oh no, this is a picture of a planetary system around a star,
Okay.
and the starlight is blocked out in the middle. And so what you see, the B, C, D, and E are big Jupiter plus size planets orbiting around that star. And it's really, I think, the first detection of a multi-planetary system, direct measurement of it.
This is the first picture of a solar system ever taken since Galileo took a picture with his pen
How do you do
400
that?
years ago.
It's just this time lapse
you
or
can
what?
actually, over time,
Yeah.
watch those go on. I've seen movies, and you
Yeah.
can watch those planets go around. I mean, that's
Wow,
one of the,
that's really
for me,
interesting.
that's one of the classic sort of, you'll see that in textbooks because it's the first, for a long, long time to come.
Yeah.
And that picture came from Summit of Mauna
And
Kea.
it confirms a lot of what we've been thinking.
Mhm.
There it is. This is
Right.
the real deal.
And the technology behind that is scary complicated, but it's a testament to Mauna Kea as a site and the technology on that telescope.
Okay, what do we got here?
The history of the universe.
Awesome.
From the Dark Ages.
That's right.
From,
There's
from
this-
what is it, the first thing?
So on the left
Inflation.
on the left is the Big Bang itself.
Yeah.
And don't ask what's to the left of that. That's a philosophical conversation that we can talk about later.
Alex Filippenko talked about inflation.
Inflation, that's
when
right.
it all got bigger after the Big Bang.
There was this moment of exponential expansion in the universe that we believe happens, and we're trying to prove that. And then after that, you see sort of the blue and turquoise colors. So that's the so-called cosmic microwave background radiation. That's the point at which the universe cooled down as a gas to the point that electrons and protons could couple again, and all of a sudden all the photons could travel unimpeded through the universe, and that's sort of the last scattering surface that you see out at microwave regions. Now you see a thing called dark ages. That's when there were no stars. There was a point after which the universe was still expanding, cooling down, but it had not had enough structure to collapse stars. So, appropriately named, there was no light that you would see at that point. And then the very first stars to the right of that, and that's the point that TMT is pushing for, from the far right all the way back to the Dark Ages, and the type of capabilities that we're talking about.
This sounds like Star Trek. I mean, how do you get back there? Does you get a special telescope that looks, I saw it on Superman once. You go around the world in reverse faster and faster and you get back to the old time. Okay, what's this?
So that's an image very close to that age that Doug just described. It's the faintest galaxy or farthest galaxy ever discovered, broke the record. And it was using, you were talking about the cool technology on the mountain. It's using one of our most advanced instruments called MOSFIRE, multi-object spectrograph, for infrared exploration. And just last week, I think this press release went out with this result. And in the wider view, that area that it's looking at looks just blank. But if you stare at it long enough with a very sensitive instrument, you can see what's there, and you can measure the color of the object, which says how fast it's moving away from you, and therefore how far away and how far back
You
in
learn
time.
a lot with these instruments.
Right.
So what's that now?
Oh, okay, so this is a result from the black hole at the center of the Milky Way. And I think it's 4 million solar masses.
right.
So those dots are observations of stars that are orbiting around the black hole. You can't see the black hole, it's
That
black.
little star in the middle is where we believe it's hiding, but there's no light, of course, because it's a black hole.
Of course.
So Andrea Ghez and our colleagues at UCLA have been studying this for years and taking positions of those stars over time and mapping them out and realizing that they're orbiting around this black hole. And just from the physics of it, you can guess as to how massive it is.
Incredible to find these things, you know, from Earth.
Yeah, exactly.
And go into the logic that takes you there. You want to say something, Doug?
Oh, I was simply going to say that there's a really neat experiment that involves the radio facilities on Mauna Kea called the Event Horizon Telescope, and the data is being recorded now. It's an interferometer that spans the entire diameter of the Earth, and it will be our first ever attempt to actually image a black hole, to take a picture of a black hole. Its resolution is that high. And I'm told that the data should be released in a year or two. It's a very complicated experiment to conduct. But that's, you know, another example of chicken skin science, where you don't have to rely on Hollywood to show you what a black hole. Thanks to this technology, and because Mauna Kea geographically is unique in this network, we're going to have the first picture ever of a black hole.
I hope it's not just a black picture.
No, actually, it's predicted to have a little fuzz and a little radiation associated, but that's another conversation. It shouldn't be black if we've got our theory right.
This is the Keck day
This
crew
is on the top Mauna Kea.
on the top of Mauna Kea. So these science results can't happen without the hard work of many professionals.
It's so much fun to be there and see all that.
In fact, many of these gentlemen up there are working right now on the summit, getting ready,
Watching
putting the
you.
finishing
Watching their boss
touches.
on TV.
Hopefully they're getting the telescope ready.
I'd like to connect with them with Skype.
That would be,
You guys could be there, you know, and
That'd be
we'll take
terrific.
a walk around by Skype. That would be fabulous.
yeah, we're extremely proud of our day crew. And here's, we talked about the 36 segments, and this is one of the segments being exchanged for maintenance, and some of the crew working
You
on
have to
that.
maintain everything, don't you? Yeah. Well, let's talk. We only have a minute or two left, and I wanted to ask my ultimate question: is what is this is sort of the title question? What is the future of astronomy on Mauna Kea and in Hawaii? And please, you know, tell me how this TMT protest affects that, how it affects it so far, and how it could affect it one way or the other on a kind of differential in the ghost of Christmas future, if you will. You know, take a chance at that.
So I still remain upbeat that we will find a solution somehow through the type of dialogue that we're involved in and trying to promote. I think it's important to realize that TMT is, as I think you've sensed in the excitement that we've shared, is a game changer from the standpoint of securing for Hawaii this sort of world-class, world-leading contribution to society. If TMT does not go forward, it's going to have all kinds of knock-on effects for the other observatories. There are some that are going to be reconfigured to basically work in conjunction with TMT, but more than that, having gone through this whole permitting process as defined by the state of Hawaii, and if it still isn't allowed to go forward, it makes it very difficult to secure funds for other projects downstream. And as a director, and perhaps the most important job I have is to find money for our observatory somehow. That makes it almost a daunting process to convince potential federal funding agencies that will be able to avoid what happened at TMT.
Grantors will say, well, you dotted all the I's, crossed the T's, and you couldn't do it, so how do we know in the future you'll be able to do it? This is a place without regard, without respect for the rule of law. We're not going to deal in that place. And I mean, I think that's a legitimate concern on their part and on your part.
Well, we're working through the issue. It's a very complicated one. It's one that I think requires a lot of conversation, a lot of listening, a lot of sensitivity. I certainly feel that. I'm very eager to work with the component of our society, the Native Hawaiians who view it as a sacred site, because that's very personal. It's very important that we factor that in. And I'm convinced that there's going to be a path forward that allows this coexistence that I mentioned before to in fact be found.
Okay, Rich?
Yeah, agree with Doug, and as a nearly lifelong resident of Hawaii, born here, it's really important to me. I think it's a important issue for the state of Hawaii, the people of Hawaii, that we find a positive way forward where all perspectives are valued and represented. Because if we go win-lose
Right.
in either direction, it's going to really divide our community. It's not going to be very positive for anyone.
Yeah, and it's not consistent with real Hawaiian
And
values.
it's
That's
not
right.
consistent with Hawaiian values.
Yeah.
We tend to be grounded in these community arguments because we live in it, and a solution that leaves us divided is essentially a failed solution. It's
Yeah.
setting up something up downstream. So that's why we have to do the heavy lifting at the community level, to talk it through, to listen to each other, to have the sensitivity there to open up opportunities for figuring out a way forward.
I wish you well in that. I hope it comes soon, and I hope we do have astronomy in Mauna Kea and in the state of Hawaii going forward, and we don't have the kind of collateral damage or frontal damage we might otherwise have if this isn't resolved. That's Rich Matsuda, engineer at Keck Observatory, and Doug Simons, director of the Canada-France-Hawaii Telescope. I envy your jobs, you guys. Thanks for coming down.
Thank
We
you for
appreciate
having
the
us.
opportunity.
Aloha.
Thank you.
Aloha.